There is a place on earth where rain has not fallen in living memory. Not in the memory of the elders, not in the record of the instruments planted there by scientists, not in the soil itself, which has forgotten what moisture feels like. The Atacama Desert in northern Chile is so profoundly dry that certain corners of it have not seen measurable rainfall in more than 4 centuries. The rocks are bare. The air carries nothing. The ground gives back nothing. And yet, if you know where to look, if you have the patience to trace the faint outlines that satellite imagery reveals in the right season, at the right angle, you will find them. Field systems, irrigation channels, the undeniable geometry of deliberate cultivation, pressed into a landscape that should be incapable of supporting life. Someone grew food here, not once, not as a desperate gamble, but generation after generation, across centuries of documented habitation. Thousands of people ate from this ground. They stored their harvests, they planned their seasons, they chose their crops with the care of people who understood exactly what the land could give them, and somehow coaxed it to give more. The question is not how they survived. Survival is a simple enough story, built from desperation and luck. What happened in the Atacama, in the frozen highlands of Tibet where barley grew before cold-resistant varieties were ever imagined, in the volcanic rock fields of Hawaii, where native farmers cultivated sweet potatoes from raw lava without importing a gram of soil, none of that was survival. It was mastery. In Tibet, ancient farmers worked at altitudes where the oxygen thins and the growing season shrinks to a narrow window of warmth between killing frosts. They grew barley, not occasionally, consistently. In the Bolivian Altiplano, where salt flats stretch toward a horizon that offers no shade and no mercy, raised bed agriculture once produced harvests that modern agronomists studying the remnants still cannot fully account for. The math does not work. The conditions do not allow for what the evidence clearly shows happened. This is not mythology. The remnants are physical. The channels are carved into real stone. The pollen is preserved in real sediment. The storage chambers are real rooms, engineered by real hands. And most of what those hands knew is gone. Not misplaced. Not waiting in some unopened archive. Gone. The knowledge of how food was grown in the impossible places of this world was buried sometimes by time, sometimes by something far more deliberate, and the question of where it went is the one this story has come to ask. In 1995, a team of archaeologists working in the Peruvian highlands uncovered a network of underground water channels carved directly through bedrock. The discovery itself was not unusual. Ancient irrigation systems had been found across the Andes for generations. What was unusual was what happened when the researchers measured the channel's angles. The gradient, the precise downward slope that determines how fast water moves through the system, had been calculated with an accuracy that matched modern hydraulic engineering standards. Not approximately. Not within a reasonable margin of error. Matched. These were people who possessed no metal tools capable of refining stone to that precision, no written mathematical tradition that we have recovered, no formal engineering discipline passed down through institutions. And yet the water moved through those channels at exactly the rate that would have prevented both stagnation and erosion, across exactly the distance required to exactly the destination where crops were grown. Somebody knew something. The channels are one piece of a larger picture that archaeology has been assembling, quietly, for decades. A picture whose implications most mainstream accounts of human history still haven't absorbed. In the Sahara Desert, fossilized pollen cores extracted from ancient lake beds reveal that vast agricultural landscapes thrived there during a period now called the Green Sahara. Climate shift explains why the region dried. Climate shift does not explain the patterns in the pollen, which show the unmistakable signatures of human crop management. Deliberate planting, deliberate burning, deliberate soil preparation in a landscape that would have challenged even modern farming systems. In the Jordanian desert, grain storage facilities have been excavated from sites dating back over 3,000 years. The structures were engineered with passive ventilation systems that maintained consistent internal temperatures and humidity sufficient to preserve harvests for years. No refrigeration, no electricity, no technology beyond the precise placement of stone, the careful management of airflow, and the knowledge of what grain needs to remain viable across seasons. In the American Southwest, The Zuni people created what researchers call waffle gardens, shallow depressions sunk into the earth in a grid pattern, each one capturing and holding the microscopic amounts of moisture that a near-rainless landscape occasionally offered. It was agriculture redesigned from the ground up for a water budget that should have made agriculture impossible. These were not flukes, they were systems. Each one was taught, refined, inherited, and improved across generations. Each one solved a specific problem with a precision that the environment demanded and that the farmers delivered. And almost none of them survived into the modern era. The systems were dismantled. The knowledge that built them was buried. The question of why that happened waits at the end of this story, where it has always been waiting. For approximately 10,000 years, human beings grew food without synthetic fertilizers, without pesticides extracted from petroleum, without hybrid seeds engineered in climate-controlled laboratories, without the monoculture systems that now stretch across continents, growing a single variety of a single crop across millions of identical acres, managed by satellite and harvested by machines. For 10,000 years, civilization fed itself with something else entirely, with knowledge. The Roman Empire sustained tens of millions of people across 3 continents for centuries. The Aztec civilization, working from floating island gardens no larger than a city block, produced per-acre yields that modern agriculture has never surpassed. The ancient Chinese developed integrated farming systems, rice paddies shared with fish, managed by ducks, fertilized by the creatures living within them, so biologically complete that the soil grew richer with every passing year. These were not marginal achievements. They were the backbone of the ancient world's greatest civilizations, and they lasted far longer than the system that replaced them. Modern industrial agriculture has existed for roughly 80 years. In that time, it has degraded approximately 1/3 of all usable agricultural land on Earth. Topsoil that took 10,000 years to accumulate has been stripped from fields in a single generation of farming. Aquifers that filled over millennia are being emptied at rates measured in decades. The diversity of crops that sustained the ancient world has collapsed to a narrow portfolio of commercial varieties whose genetic similarity makes them collectively vulnerable to any pathogen adaptive enough to find a way in. The systems we call primitive lasted 10,000 years. The system we call advanced has lasted 80. And in those 80 years, it has done more damage to the foundation of human food production than all the previous centuries combined. This contrast is not a political argument. It is an observation. The people who built terraced hillsides in the Andes without metal tools, who fed desert cities without rainfall, who maintained soil fertility across 400 consecutive growing seasons, those people were doing something right, something that the world largely stopped doing within living memory, something that has not yet been fully named, let alone replaced. The ancient farmers were not sophisticated by accident. They were sophisticated because they had no alternative. They could not buy a bag of synthetic nitrogen and pour it on exhausted soil. They could not spray a compound to kill every insect that touched their crops. They had to understand the land they farmed deeply, precisely, intimately, or they starved. And so, they studied it. They tested it. They passed what they learned to their children, who refined it and passed it forward again. That body of knowledge accumulated across cultures, across continents, across millennia, is what this story is about. Not what we were taught, what we were not taught, and what it cost, and what it continues to cost, to have forgotten it. What follows is not a theory. It is not a collection of half-remembered folk wisdom dressed up in documentary language. It is a documented, verifiable, sometimes deeply uncomfortable history, one that moves through the driest deserts on Earth, through the frozen soil of the Arctic, through the deliberate burning of libraries, through corporate boardrooms, where the fate of 10,000 plant species was decided by people who had never held a seed in their hands. This story will take you into the Amazon basin, where a soil exists that is 2,000 years old and growing more fertile every single year, a substance that modern science has spent decades studying and still cannot fully explain. It will take you beneath Persian mountains, where water channels carved 3,000 years ago are still flowing today, feeding crops in a desert that should be incapable of sustaining them. It will take you into the Andes, where a farming system fed an empire of 12 million people without depleting a gram of the soil it depended on, across centuries of continuous use. And then it will follow the trail of what happened to all of this, the seed varieties that were classified out of existence, the farming communities displaced from land they had managed for generations, their knowledge dismissed as backward, and their practices replaced by systems that proved, within decades, to be fragile in ways the ancient methods never were. The agricultural libraries burned in conquest. The indigenous soil knowledge delegitimized by colonial administrators who lacked the context to recognize what they were looking at. The corporate decisions documented in memos, recorded in policy papers that removed millennia of crop diversity from the global food supply in less than a generation. This is not a story about villains. It is more complicated than that, and more instructive. Many of the people who made these decisions believed they were helping. Several of them were celebrated for it. And the consequences of their help are visible now in the degraded soils, the collapsing crop diversity, the food system fragility that researchers quietly, in the language of academic papers that most people never read, describe as one of the defining vulnerabilities of the coming century. The ancient knowledge is not entirely gone. What remains of it is the most important agricultural story of our time, and the people working to recover it are doing so against the same institutional resistance that buried it in the first place. This is where the story begins. Beneath the surface, in the ground, in the invisible, extraordinary world that ancient farmers understood and that we spent a century learning to ignore. In the 6th century of the Common Era, a Chinese agricultural scholar named Jia Sixi sat down to write what would become one of the most comprehensive farming manuals of the ancient world. The Qi Min Yao Shu translated, roughly, as essential techniques for the common people, covered everything from crop rotation to animal husbandry to the fermentation of food for preservation. But buried within its many chapters was something that modern readers, with the benefit of microscopes and molecular biology, cannot encounter without a quiet shock of recognition. Jia Sixi wrote about the invisible life within soil. He described how decomposing organic matter was transformed by something he could not see into nourishment that plant roots could absorb. He described the conditions that encouraged this transformation and the conditions that disrupted it. He was describing, with the vocabulary available to him in the 6th century, the biological activity of soil microorganisms. He was describing bacteria. He was describing fungi. 1400 years before Western science gave those processes formal names. He was not alone in knowing this. The ancient Indian text called the Vrikshayurveda, the science of plant life, classified soils into categories so specific that modern pedologists, the scientists who study and classify soil, have found direct parallels between the ancient Indian categories and their own taxonomic systems. The Vrikshayurveda described soils by color, texture, smell, and taste. It prescribed specific treatments for specific types of depleted soil, and those treatments, when analyzed in modern laboratories, proved to contain the precise biological inputs that those soils actually required. In the 1st century of the Common Era, the Roman agricultural writer Columella observed that fields exhausted by years of continuous cropping could be restored by planting them with legumes and then turning those plants back into the ground. He did not know about nitrogen. He did not know that leguminous plants host bacteria on their roots that extract nitrogen from the atmosphere and fix it into forms the soil can use. He knew only what 2 centuries of Roman farming observation had revealed, that this specific practice restored the land's ability to grow food. He was describing nitrogen fixation 1900 years before nitrogen was isolated as a chemical element. Across centuries and continents, without contact, without shared language, without the formal apparatus of scientific institutions, ancient farmers arrived independently at an understanding of soil that Western agricultural science did not formally embrace until the late 20th century. They understood that soil was not a passive growing medium. It was a living system, complex, dynamic, fragile, and extraordinary. What makes this not merely impressive but urgent is the second half of the story. All of this knowledge existed. It was written down. It was taught. It was practiced. And then, in the span of a few generations, It was set aside in favor of a simpler model, one that treated soil as a container for chemical inputs, rather than as a living ecosystem that required stewardship. What was gained in short-term yield was traded for something the ancient farmers would have recognized immediately as a catastrophic loss. The soil of the Amazon rainforest is, by almost every measure, poor. The ecosystem above it, the canopy, the rivers, the staggering biological diversity, gives the impression of extraordinary richness. But the richness lives in the cycle, not the ground. The nutrients that fall to the forest floor are consumed and recirculated so quickly that the soil itself holds almost nothing. When modern agricultural developers clear Amazonian land and attempt to farm it, the typical result is 3 years of marginal productivity, followed by collapse. The land cannot sustain what is asked of it. It was never designed to. Which makes what lies, scattered beneath the Amazon basin, one of the most disorienting agricultural discoveries of the past century. In patches across the region, some of them small, some of them stretching across hundreds of acres, there exists a soil unlike anything the surrounding forest produces. It is black, almost impossibly dark, dense with carbon, alive with microbial activity that makes the adjacent forest soil look biologically dormant by comparison. It is called Terra Preta de Indio, Indian dark earth, and it was made by human hands. The carbon dating places its creation between roughly 450 BCE and 950 CE. Pre-Columbian Amazonian civilizations, peoples whose histories were largely erased by the disease epidemics that followed European contact, created this soil deliberately, over generations, in quantities large enough to be found across enormous stretches of a continent. They created it with charred organic matter, with bone, with food waste, with materials that, when combined and introduced into the soil in ways that researchers have spent decades attempting to understand, produced a biological transformation with no modern parallel. The most extraordinary aspect of Terra Preta is not its age. It is not even its fertility, though that fertility remains remarkable 2,000 years after its creation. The most extraordinary aspect is that it is still spreading. When researchers extract a sample and remove it from the ground, the surrounding soil, over months and years, begins to convert to the same dark, carbon-rich composition. As though the Terra Preta is alive. As though it carries within it some biological instruction that teaches the earth around it what to become. Modern scientists have identified biochar-charred organic matter that creates a permanent carbon matrix in the soil as the core ingredient. They have attempted to replicate it. In laboratories with precise controls, with modern understanding of soil biology, with every tool that contemporary science provides, they have produced biochar that is impressive by modern standards, and nowhere near the biological richness of soil that was made 2,000 years ago by people who left no written record of what they knew. Something in the original process, some specific combination of materials, some timing, some technique was lost when the people who held it were lost. The epidemics that followed European contact in the Americas killed an estimated 90% of the indigenous population within a century. The Amazonian civilizations that built Terra Preta were among the casualties. Their agricultural libraries were oral, embodied, passed person to person across generations. When the people died, the knowledge died with them. What remains is the soil itself still fertile, still spreading, still demonstrating that something extraordinary was once understood. And we are standing in its shadow, holding instruments sophisticated enough to measure it, and not yet sophisticated enough to explain it. Beneath a single teaspoon of healthy soil, the kind of soil that ancient farmers built and tended and passed down through generations, there are more individual living organisms than there are human beings on Earth. Bacteria in the billions, fungi in networks that span entire fields, nematodes, protozoa, earthworms threading through the dark, mites and beetles and organisms without names in any language because they have never been formally catalogued. A single gram of living soil contains biological complexity that rivals any ecosystem visible to the naked eye. Modern industrial farmland, after decades of synthetic fertilizer application, pesticide use, and mechanical tillage, contains a fraction of that life. In some heavily managed agricultural regions, soil biology has been reduced to near zero. The earth functions as a chemical substrate, holding plants upright, while nutrients are delivered by application rather than by biological process. It grows food. For now, but it is not living soil anymore. It is, in the precise and meaningful sense of the word, dirt. Ancient farmers knew the difference. Not in the language of microbiology. They had no microscopes, no petri dishes, no way to observe what they were managing. But they observed outcomes, and across generations, they identified the practices that produced extraordinary harvests year after year, and the practices that exhausted the land. The distinction they arrived at, stated differently in every culture, but pointing at the same truth, was this: the soil must be fed before the plant can be fed. In the traditional Japanese system of Satoyama farming, forest leaf litter was gathered each autumn and applied to agricultural fields. Not for its nutrient content alone, but for the microbial communities it carried the biological life of the forest floor, transplanted into the farm. In Rwanda, traditional farming practice involved the careful timing of specific green plants grown, cut, and worked into the soil in a precise sequence to feed the microbial community before any crop seed was planted. In Korea, plant materials, fish scraps, and grain husks were fermented together in clay vessels, and the resulting liquid was applied to both soil and plant surfaces as a probiotic inoculant. Modern laboratory analysis has confirmed it delivers beneficial microorganisms that suppress disease and stimulate growth. The modern equivalent to what these farmers built over millennia is the human gut microbiome. A healthy gut does not merely process food mechanically. It hosts a community of trillions of organisms whose collective activity digesting, synthesizing, regulating produces health outcomes that no pill, no supplement, and no pharmaceutical intervention can fully replicate. Damage that community, and the downstream consequences are complex and long-lasting. The parallel is not metaphorical, it is structural. Modern industrial agriculture has been applying the equivalent of intravenous feeding to a patient whose digestive system is quietly dying. The food keeps being produced, the system keeps functioning, and the foundation beneath it, the living community that made all of it possible, has been diminishing, season by season, in ways that are only now beginning to register as an emergency. Beneath the forest floor, connecting the roots of trees that may stand hundreds of meters apart, there is a network. It is built from fungal threads thinner than a human hair, branching and reconnecting across distances that span entire ecosystems. Through these threads, trees share sugar, they share water, they send chemical signals when insects attack, allowing their neighbors to prepare defensive compounds before the insects arrive. Parent trees direct nutrients towards struggling seedlings that share their genetic lineage. The network maintains the health of the whole by allowing any part that has surplus to support any part that is in need. Scientists began formally mapping this network in the 1990s. They called it, with a nod to its scope and complexity, the Wood Wide Web. It was described in academic journals as a discovery, and in the strict sense of formal Western science, it was. But in another sense, one that requires looking at what ancient farmers built, rather than what modern scientists wrote, it was a rediscovery of something that had been managed deliberately for thousands of years. The Andean practice of Minca farming, communal cultivation, in which multiple species were planted together in intimate proximity, their roots intermingling, creates, as mycologists now understand, precisely the conditions that allow mycorrhizal networks to develop most robustly. The milpa system of Mesoamerica, planting corn, beans, and squash together, does not merely divide the above-ground space efficiently. Below the surface, it creates a fungal web linking all three species in a mutual exchange that makes each of them more productive than any of them would be in isolation. In the eastern woodlands of North America, indigenous farming communities incorporated wild plants from nearby forest margins into their cultivated fields. European colonizers who observed this practice described it as sloppy evidence of a people who did not understand the value of a clean, organized field. What modern mycology understands is that those wild plants were seeding the mycorrhizal community. They were establishing the underground network that the food crops depended on for nutrient access, disease resistance, and drought tolerance. Conventional industrial farming attacks the mycorrhizal network from multiple directions simultaneously. Deep tillage breaks the fungal threads. Synthetic nitrogen makes it unnecessary for plant roots to maintain fungal partnerships, causing those partnerships to atrophy. Fungicide applications kill the very organisms that the network is built from. And all of this damage is invisible, happening underground, accumulating across seasons without any single event dramatic enough to register as a loss. The ancient farmers who planted in mixtures, who preserved the wild margins of their fields, who refused to till more deeply than their experience, suggested they were protecting something they could not see. They were right to do it. Stand in the Negev desert in the middle of July. The air temperature rises past 40 degrees before noon. The sky is the blue of bleached bone, not a cloud, not a shadow, not a suggestion of relief. The ground beneath your feet has been receiving, on average, 100 millimeters of rain per year for as long as anyone has been measuring. 100 millimeters. Less than 4 inches. Wheat requires 400 millimeters to grow. The mathematics of survival in this landscape suggest that no significant human population should have been able to sustain itself here. The numbers simply do not add up. And yet, 2,000 years ago, a city called Petra stood in the heart of landscape like this, not on its margins, not in some fortunate microclimate where water pooled by accident, but in the full severity of Negev-adjacent desert, and it was home to 30,000 people. Not a temporary encampment, not a trading post sustained by imported supplies, a city. With markets, with temples, with roads, with a governing civilization sophisticated enough to maintain diplomatic relations with Rome. 30,000 people living in a desert, eating food grown in a desert for over 6 centuries. The Atacama in Chile presents the same impossible arithmetic. Some weather stations positioned in its driest zones have never recorded a rain event. Not in living memory. Not in the recorded history of the instruments. The stone is bare and ancient and indifferent to the logic of crops. And there, too, archaeologists have found the outlines of agricultural fields, channels, storage chambers. The evidence of deliberate, sustained cultivation. In the Thar Desert of Rajasthan, where 2 consecutive drought years occur on average once a decade, and where the sun strips moisture from exposed ground within hours of any rain that does fall, ancient communities built field systems that captured, distributed, and stored water with an efficiency that modern irrigation projects in the same region have not managed to equal. These discoveries are not isolated. They are not archaeological curiosities found once and explained away. They form a pattern found across the driest places on Earth, pointing toward a body of knowledge so effective that it allowed human civilization to establish itself and thrive in environments where modern agricultural science regards food production as impractical. The knowledge was not magic. It was not supernatural. It was practical, empirical, hard-won understanding of how water behaves where it hides, how it moves, what it needs to be guided from where the land offers it to where the crops demand it. And the people who possessed it solved a problem that the modern world, with all its engineering capacity, is still struggling to solve. Water scarcity is the defining agricultural challenge of the coming century. The ancient farmers who grew food where rain never came built the playbook for surviving it. Most of that playbook is unread. Somewhere beneath the Iranian plateau, carved through solid rock by hands that worked without steel, without dynamite, and without engineering blueprints of the kind modern construction requires, there are channels that have been carrying water for 3,000 years. Not occasionally, continuously. The water enters from an aquifer in the mountains, flows through a gently sloping underground tunnel. The slope, calculated by eye and by accumulated knowledge across a distance that sometimes exceeds 50 kilometers and emerges at the other end in a desert agricultural lowland that would be barren without it. No pump, no electricity, no maintenance that requires anything more sophisticated than a person with basic tools doing periodic repairs. The Qanat, from the Arabic word for channel, is one of the most elegantly functional pieces of engineering in human history, and it transformed roughly 1 million hectares of Iranian desert into productive farmland at its peak, sustained by a network of approximately 50,000 individual systems spread across Persia, Afghanistan, and North Africa. The design principle is almost deceptively simple. The water source, a mountain aquifer, recharged by snowmelt and seasonal rain at elevation, sits higher than the destination where water is needed. A mother well is dug to reach the aquifer. From that well, a tunnel is excavated on a precise downward angle, gentle enough that the water does not accelerate into erosive turbulence, steep enough that it flows without stalling. Along the length of the tunnel, vertical shafts are sunk from the surface, each one serving as a construction access point during building, a ventilation portal during operation, and a maintenance window for the lifetime of the system. The result is a gravity-fed river that runs entirely underground, protected from evaporation, self-pressurizing, and self-regulating. When the mountain aquifer receives heavy snowfall, the Quanat carries more water. In dry years, it carries less, but it never stops entirely as long as the aquifer holds. It operates within the natural budget of the landscape. It does not borrow from the future to pay for the present. Modern hydrological engineers, who have studied Quanat systems in detail, describe them with a specific kind of professional admiration, the recognition of a solution so well matched to its problem that it is genuinely difficult to improve upon. Some of the Quanats still operating in Iran today are the original structures. They have been maintained by local communities across 3,000 years of political change, conquest, drought, and upheaval. The engineering has outlasted every empire that has passed through the region. The political lesson embedded in the Quanat's history is as instructive as the engineering itself. When Alexander the Great's successors took control of Persia, they attempted to impose a tax on the skilled workers who maintained the Quanat systems, the people whose inherited knowledge kept the channels flowing. The workers refused. A revolt followed. The disruption in maintenance that resulted was brief by historical standards, but devastating in its effects. Regions that had been productive for centuries began to dry out within a single generation. The farmland that had been sustained by 3,000 years of accumulated engineering knowledge could not survive a single decade of political interference with the people who held that knowledge. This pattern, political disruption, leading to the rapid collapse of agricultural systems that had been stable for centuries, would repeat itself across history. It repeats in the Maya collapse, in the Nabatean story that unfolds later in this chapter, in the colonial dismantling of indigenous farming communities across 3 continents. The engineering can be extraordinary, but the knowledge required to maintain it is more fragile than the stone it carves through. Every night, even in the driest desert, the air changes. Temperatures drop. The stones that absorbed heat through 16 hours of relentless sun begin to cool, and as they do, the water vapor suspended invisibly in the desert air reaches its dew point, the temperature at which vapor becomes liquid. Droplets form on cold surfaces. They bead on rock faces, on coarse pebbles, on the undersides of leaves. In most desert landscapes, these droplets evaporate again within minutes of sunrise. They are too small, too scattered, too brief to matter, unless someone has been designing the landscape specifically to capture them. On hillside slopes in the Negev, archaeologists identified something that initially appeared to be an unremarkable agricultural feature: rows of small stone mounds arranged at regular intervals across the gradient of the hill. They were too small to be field boundaries. They were the wrong shape for graves. Some researchers suggested they were early survey markers. Others found no explanation that satisfied the evidence. Then, someone looked more carefully at the base of each mound, where the gravel was arranged in subtle concave patterns, and at the channels between the mounds, angled at almost imperceptible gradients toward planted areas below. The stone mounds were dew collectors. Each night, they accumulated condensation on their surfaces. That moisture was channeled, microdrop by microdrop, downslope to the specific plants selected to receive it: olive trees, fig trees, grain varieties with root systems trained over generations to reach deep into the soil for water that had soaked in during the night. The system produced no dramatic irrigation event. It produced a slow, steady, invisible supply of atmospheric water, night after night, season after season, sufficient for the specific crops and the specific yields that the farmers had calibrated their system to achieve. In coastal Peru, the pre-Inca civilizations of the Lomas landscapes built stone terraces, not primarily for growing the terraces themselves, were covered with coarse gravel selected for its thermal properties. Each night, Pacific fog rolled inland from the ocean. The gravel absorbed the fog's moisture. The water trickled through the terrace structure into cisterns below, where it was stored for distribution to growing areas. The amount of water captured per terrace per night was small. Across a network of terraces operating simultaneously across a hillside, it was sufficient to sustain agriculture in a landscape that received almost no direct rainfall. The Canarian people of the Canary Islands went a step further. They planted trees, not for food or timber, specifically for water collection. The tree canopies intercepted fog moisture, which condensed on leaves and branches dripped to the ground, and was channeled to collection systems that produced thousands of liters of water daily from forests that were, in their essential function, living weather capture infrastructure. In 2019, a company based in Chile received attention for installing fog nets in mountain communities, mesh panels that capture atmospheric moisture and deliver it to villages without conventional water access. The technology was presented as a modern innovation. The company was not wrong to be proud of it. The principle they had implemented was 2,000 years old, encoded in stone terraces and ancient orchards, waiting for someone to look at the right hillsides and ask the right questions. The Nabateans do not receive the recognition they deserve. History tends to remember them primarily as traders, the people who controlled the incense routes of the ancient Near East, who grew wealthy on commerce passing between the Mediterranean world and Arabia. Their capital, Petra, is remembered for its architecture, temples and tombs carved from rose-colored sandstone, photographs of which have populated travel brochures for a century. What receives far less attention is the system that kept 30,000 people alive in a desert, receiving less rain per year than some cacti require. The Nabatean water system was not a single engineering achievement. It was a philosophy of water made physical, implemented at every scale across a landscape that offered almost nothing, and was persuaded, by centuries of accumulated knowledge and infrastructural investment, to offer enough. Every hillside surrounding the agricultural valleys had been shaped. Hillside cisterns, some of them enormous, some of them intimate, had been carved into rock faces at precisely calculated positions to intercept flash flood water from the rare violent rainstorms that swept through the region every few years. These storms, when they came, were dangerous without management torrents, capable of stripping soil and destroying crops. With management, they were the annual water budget. Every drop was caught, directed, stored. From the cisterns, water moved through a network of stone conduits, built on gradients engineered to maintain flow without erosion. Underground pipes, sections of terracotta, joined with hydraulic lime, distributed water across terraced agricultural fields, where every micro-drainage channel had been designed to slow runoff, give it time to infiltrate the soil, and prevent evaporation. Researchers who have analyzed these systems estimate that Nabatean water efficiency per acre exceeded what modern precision drip irrigation achieves in comparable desert climates. They fed a city for 600 years in a desert, and then the Romans arrived. In 106 CE, the Roman Empire annexed Nabatea. They inherited a functioning civilization, a profitable trade network, and a water system of extraordinary sophistication. The Romans were, by any measure, the greatest engineers of the ancient world. Their aqueducts, roads, harbours, and public buildings demonstrate a mastery of large-scale construction that has rarely been equalled, and they could not maintain what the Nabateans had built. The failure was not one of effort or investment, it was one of understanding. The Nabatean system was not a collection of structures. It was a living relationship between infrastructure and landscape, maintained by communities whose knowledge of how to read the watershed, how to anticipate the storm, how to adjust the conduit gradient for a season of unusual rainfall, was embedded in their daily practice. That knowledge was oral, behavioral, and local. It could not be read from a blueprint because no blueprint existed. It existed in the farmers themselves. Within 3 centuries of Roman administration, most of the Nabatean water infrastructure had fallen into disrepair. The agricultural terraces eroded, the cisterns silted. The farmland that had supported a thriving desert civilization reverted, field by field, to the barren landscape it had been, before the Nabateans spent 600 years teaching it to be something else. The conquering civilization, the more powerful civilization was In every relevant way, the less capable one. At some point in the last 12,000 years, human beings have deliberately cultivated approximately 10,000 plant species for food. 10,000 distinct species, each one selected, propagated, refined, and adapted to specific growing conditions by farmers who understood, through direct and accumulated experience, what each plant needed and what each plant could give. The diversity of that ancient food system is difficult to hold in the imagination. It is easier to approach from the other direction. Today, 75% of global food calories come from 12 plant species. 3 of those 12, wheat, rice, and corn, account for more than half of everything humanity eats. We have traveled from 10,000 to 3 in the span of a single century. In the highlands of Peru and Bolivia, ancient Andean farmers maintained over 4,000 distinct varieties of potato, not 4,000 arbitrary variations, 4,000 precisely adapted cultivars, each one suited to a specific altitude, a specific rainfall pattern, a specific soil type, a specific frost exposure. Together, they constituted a food system of extraordinary resilience. If blight struck the varieties suited to lower elevations, the highland varieties remained unaffected. If drought struck one region, the drought-tolerant varieties from arid microclimates continued producing. No single disease, no single weather event, no single catastrophe could touch all 4,000 simultaneously. The Irish potato famine of the 1840s has been analysed as a political catastrophe, as a colonial failure, as a story of poverty and power and deliberate neglect. All of those analyses contain truth. But at its biological root, it was something simpler and more instructive. Ireland's entire potato crop had collapsed to a single variety, the Irish lumper. When the Phytophthora infestans pathogen found it, the crop had no biological defense. One variety, one pathogen, one famine, 1 million people dead, another million forced to leave their homeland forever. In the Andes, at exactly that same moment, the farmers who maintained 4,000 varieties of potato continued their harvests. There is no record of a catastrophic Andean potato famine during the 19th century. The system their ancestors had engineered specifically to prevent one held. The Andean farmers did not create 4,000 potato varieties by accident, by aesthetic preference, or by the kind of organic cultural drift that sometimes generates diversity without intention. They created them deliberately. The diversity was a design feature, a biological redundancy built into the food system, the way structural redundancy is built into a bridge. The bridge does not need every cable to bear the full load at once, but if one cable fails, the others absorb the difference. No single point of failure can bring the whole structure down. The ancient potato farmers of the Andes understood this principle with a precision that modern food system designers, working with computers and climate models, are only now beginning to recover. They called it farming. We call it, in the technical language of systems engineering, resilience. It is one thing to speak of diversity as an abstraction. 10,000 species, 4,000 varieties, numbers too large to feel personal. It is another thing entirely to talk about specific plants. Real plants, with real histories, carrying real properties that no modern variety has inherited and no modern breeding program has yet reconstructed. Emma wheat was the grain that built Egypt. The pyramid workers who raised the great monuments of Giza, tens of thousands of people, laboring across decades, were fed primarily on bread made from emma. Their skeletal remains, analyzed by modern researchers, show a protein intake profile distinctly different from populations consuming modern bread wheat. Emma's protein is structured differently, more digestible for many people, and more compatible with gut microbiomes that have not evolved alongside the intensively hybridized gluten profiles of modern wheat. Emma also grows without synthetic fertilizer, in nutrient-poor soils, at a fraction of the input cost of modern wheat varieties. It was set aside not because it was inferior, but because it produced lower yields per acre when measured by the single metric that the industrial food system applies to everything. Bere barley is grown on fewer than 50 farms in the world today. It was cultivated continuously for 5,000 years on the coasts and islands of Scotland and the Orkney Islands, environments so cold, wet, and low in sunlight that modern barley varieties will not germinate in their soil bere will. It has been adapted, through 50 centuries of selection, to conditions that no other known barley can tolerate. If those conditions which describe a significant portion of northern European coastal land ever need to be farmed again, there are fewer than 50 farms on Earth still holding the knowledge of how. Mandan corn was developed by the Mandan people of the northern plains for a growing season so short that modern hybrid corn varieties cannot complete their life cycle within it. Mandan corn produces a harvestable crop in 60 days, compared to 90 to 120 days for commercial varieties. In a world of unpredictable frost events and shortened growing windows, that 60-day cycle is not a historical curiosity. It is a survival tool. Every one of these varieties carries within its genetics the memory of thousands of years of adaptation to specific conditions. That adaptation took millennia to accumulate. It cannot be reverse engineered in a laboratory in a generation. When a variety disappears from cultivation, it takes that accumulated memory with it. The drought tolerance, the pest resistance, the nutritional profile, the ability to grow in conditions that its more commercially successful replacements simply cannot handle. The varieties that were left behind were not the weakest. They were not the failures of agricultural history. In many cases, they were the most remarkable achievements of it. They were simply inconvenient for a system that had decided, at the beginning of one particular century, that yield per acre in optimal conditions was the only question worth asking. Between 1,900 and 2,000, approximately 75% of the genetic diversity in the world's food crops disappeared permanently. This is a documented figure from the United Nations Food and Agriculture Organization. It is not a contested estimate or an activist projection. It is a measurement. 3/4 of the genetic heritage accumulated across 12,000 years of human agriculture gone in one century. It did not happen all at once. It happened through a process so incremental, so distributed across so many individual decisions by so many organizations in so many countries, that its cumulative effect was invisible until it had already become irreversible. The Green Revolution of the 1950s through the 1970s was, by the standards it set for itself, a success. Norman Borlaug's high-yield wheat varieties, combined with irrigation infrastructure and synthetic fertilizer, dramatically increased harvests in South Asia and Latin America, during a period when demographic projections genuinely suggested that mass famine was inevitable. Millions of lives were preserved. The Nobel Committee awarded Borlaug its Peace Prize. The gratitude was not misplaced. But the mechanism by which the Green Revolution was implemented carried a cost that its architects did not fully reckon with. The high-yield varieties required specific inputs to perform as promised. They needed synthetic nitrogen. They needed pesticides. They needed irrigation infrastructure. Farmers who adopted them entered a cycle of input dependency that traditional varieties adapted over centuries to perform on what the local land and climate naturally provided had never required. International development organizations made the calculation that traditional variety replacement was not merely acceptable collateral damage, but an active policy goal. Access to credit, to subsidized inputs, to agricultural support programs was frequently conditioned on the adoption of approved varieties and the discontinuation of traditional ones. Farmers who chose to retain their heritage varieties found themselves excluded from the economic structures that made farming viable in the modern world. Within a generation, the market for traditional varieties had collapsed. Without market demand, farmers could not afford to grow them. Without cultivation, the varieties ceased to exist. Many of them had never been formally collected by any seed bank. They existed only in active cultivation, in farmers' hands, in the knowledge of how to grow them season by season. When the farmers stopped growing them, the varieties, some of them thousands of years old, vanished without a scientific record, without a preserved sample, without any documentation of what they contained or what they could have offered. The people who made the decisions that produced this outcome were not acting maliciously. Several of them were acting with genuine humanitarian conviction. The tragedy of this particular story is not that it was perpetrated by villains. The tragedy is that it was perpetrated by people who were measuring the right thing badly, optimizing for short-term yield in optimal conditions, while failing to account for the value of resilience, of adaptation, of the biological memory encoded in genetic diversity that takes millennia to accumulate and a single generation of neglect to lose forever. In the autumn of 1941, German forces laid siege to the city of Leningrad. The siege would last 872 days. During that time, approximately 1 million people in the city would die of starvation, one of the most devastating civilian famines produced by deliberate military action in modern history. In the streets, people collapsed from hunger. In apartments, families divided portions so small they extended life without sustaining it. In a building on Herzen Street, behind locked doors, sat the Vavilov Institute of Plant Industry, one of the most extraordinary seed collections in the world. Assembled across decades by the botanist Nikolai Vavilov and his colleagues through expeditions to every agricultural region on Earth. The collection contained hundreds of thousands of seed samples, representing thousands of plant species, potatoes, grains, legumes, fruits, many of them varieties found nowhere else on the planet. The scientists inside the institute were starving, and they did not eat the seeds. 11 of them died of starvation while working to protect the collection. They understood, with the clarity that sometimes comes at the end of things, that the seeds in those drawers were irreplaceable. Not more valuable than their lives in any abstract ethical sense, but irreplaceable in a way that made consuming them, even in the extremity of what they were experiencing, feel like a betrayal of something larger than survival. They were custodians. The seeds were not theirs to eat. The Hopi Nation of Arizona has maintained continuous cultivation of specific corn and bean varieties for over 2,000 years. Through displacement, through drought, through the sustained pressure of colonial systems that regarded traditional crops as backward and offered economic incentives to abandon them, Hopi farmers preserved specific seed lineages across more than 100 generations of cultivation. The seeds are ceremonially managed, passed according to protocols that ensure both their biological viability and the cultural knowledge required to grow them correctly. The two, the seed and the knowledge, are understood to be inseparable, because they are. In France, an organization called Cocopelli has spent decades collecting, propagating, and distributing heritage seed varieties. In 2005, it was prosecuted by French authorities for distributing unregistered vegetable varieties, plants so old that they predate the regulatory systems designed to certify them, now legally defined as products that cannot be legally sold, ancient seeds, classified as contraband. These stories, the scientists who starved for seeds, the farmers who grew the same corn their ancestors grew 2,000 years ago, the seed savers prosecuted under laws that classify heritage vegetables as illegal, share a single underlying recognition. The people in each story understood something that institutional systems consistently fail to recognize: that a seed variety, once gone, cannot be recalled; that the knowledge of how to grow it, once lost, cannot be reconstructed; that the biological heritage accumulated across thousands of years of agricultural civilization is not an archive. It is a living thing, and it survives only as long as someone is tending it. 60 meters below the surface of the Cappadocian Plain, in central Turkey, carved into the soft volcanic rock of a landscape that looks, from above, like an ordinary Anatolian plateau, there is a city. Derinkuyu, its name meaning deep well in Turkish, descends through 18 levels of excavated chambers, stables, churches, storage rooms, and communal spaces. It held, at its peak occupation, an estimated 20,000 people. And scattered among its deeper levels, researchers have found something unexpected: rooms with grooves cut into their stone floors. Shallow channels, too precise and too regularly spaced to be drainage. The kind of channels that would be designed, in a surface farming context, to direct water across a growing surface. People were farming underground, in complete darkness, 4,000 years ago, and they were doing it deliberately enough to engineer irrigation infrastructure into the stone itself. The Saharan Tuareg people built underground passage systems, fogaras, that served not only as water conveyance channels, but as growing environments. In the stable, humid darkness of these underground passages, root crops and fungal food sources were cultivated with a consistency that surface growing in the Sahara could not have achieved. The temperature underground held steady, regardless of what the surface temperatures were doing. The humidity maintained itself. The growing conditions that the plants required were built into the geological fact of the Earth. In the lowest plateau of China, entire cliff faces were honeycombed with agricultural chambers. The soft, wind-deposited soil of the plateau could be excavated with relative ease, and ancient farmers took advantage of that ease to create underground growing environments for mushrooms, root vegetables, and germination chambers for grain. The chambers maintained consistent moisture levels through the natural properties of their loess walls that absorbed and released humidity in a cycle that prevented both desiccation and rot. The engineering was not mechanical, it was geological. The farmers used the Earth's own properties as their climate control system. Underground farming solves a specific set of problems that surface farming cannot avoid. Frost cannot reach crops buried below the freeze line. Hail cannot damage plants growing in stone chambers. Drought affects the surface, while underground moisture reserves, maintained by capillary action through the surrounding rock and soil, continue to supply root systems that have been positioned to reach them. The catastrophic weather events that destroy surface harvest the late frost, the early drought. The unseasonable heat pass harmlessly over the heads of underground farmers who have placed their crops beyond the reach of the sky. The ancient farmers who built these systems were not retreating from the surface world out of fear or limitation. They were engineering redundancy into their food supply. They were creating a backup, a growing environment that operated on different principles from their surface fields, so that a catastrophe that destroyed one could not simultaneously destroy the other. They were thinking about agricultural resilience with a sophistication that modern food system designers are still working to match. At 4,000 meters above sea level, the air is thin enough that a person unaccustomed to the altitude will feel the effort of walking as though they are moving through resistance. The sky is a darker blue than anything visible from sea level. The temperature drops sharply after sunset, falling below freezing on nights that follow afternoons of intense, unfiltered sun. The growing season, compressed between the last frost of spring and the first frost of autumn, lasts weeks, where lower elevations measure their growing windows in months. The Inca Empire chose to farm here, not in spite of these conditions within them, with a thoroughness that transformed challenge into advantage. What they built in the mountains of the Andes remains. 4 centuries after the civilization that created it was dismantled by conquest and epidemic, among the most sophisticated agricultural infrastructure on Earth. The Andeans, the terraced hillside systems that step across Andean slopes like enormous stone staircases, are typically described as erosion control measures. This description is not wrong, but it is vastly incomplete. The terraces were not simply cut into hillsides to keep soil from washing away. They were engineered as microclimatic systems, designed with a precision that was not apparent until modern researchers began measuring what the stone walls actually do. The walls retain heat. Through the day, they absorb solar radiation. Through the night, they release it slowly back into the terrace interior. The temperature differential between a functioning undane terrace and the surrounding open mountainside can reach 3 degrees Celsius. In the context of high-altitude agriculture, where a single unexpected frost can destroy an entire season's work, 3 degrees is an agricultural lifetime. It is the difference between a crop that completes its reproductive cycle and a field of blackened stems. The terrace fill, the material packed into the terrace structure behind the retaining wall, was not simply whatever soil was locally available. Researchers excavating restored Incan terraces have found deliberate layering, a base of large stones for drainage, followed by smaller gravel, followed by fine particulate material, followed by topsoil. Each layer was chosen to manage water movement within the terrace in a specific way, draining excess moisture quickly enough to prevent waterlogging, retaining capillary moisture long enough to sustain root systems through dry periods. The crops selected for these extreme environments were themselves the product of thousands of years of altitude-specific breeding. Potato varieties that could survive ground temperatures below zero were cultivated at elevations where no temperate zone crop could exist. Quinoa, strains that thrived in both waterlogged and drought conditions, were maintained as insurance against the unpredictability of mountain weather. The Incan agricultural system at high altitude was not a compromise with a difficult environment. It was a mastery of it, a mastery so complete that the infrastructure built to achieve it has survived half a millennium of abandonment and remains partially functional where it has been restored. The ground in much of Siberia is frozen. not seasonally permanently, in the deep layers, with only the surface thawing briefly each summer before the cold returns and reclaims what the brief warmth had softened. This is permafrost soil whose temperature has remained below zero continuously, in some cases for tens of thousands of years. Modern agricultural science regards it as effectively unfarmable. The growing window is too short, the soil biology too suppressed. The energy required to produce a meaningful harvest in such conditions is not recoverable from what the harvest yields. Archaeologists working in Siberia have found the remains of cultivated plants, not wild species. Cultivated varieties, root vegetables, and grain plants that show the morphological signatures of deliberate human selection over multiple generations, found at latitudes where modern agriculture has given up. Alongside these plants, they found charred soil patterns, deliberate burning of permafrost surface layers in defined geometries, circular patches, elongated strips, grid patterns, the kind of burning that has a specific agricultural purpose. When soil scientists analyzed similar burning patterns in other Arctic contexts, they found something that connects this practice directly to the terra preta story encountered in the Amazon. The charred surface layer, created by deliberate burning, behaves, on a micro scale, like biochar. It darkens the soil surface, increasing its capacity to absorb solar radiation and retain heat. It creates a chemical environment that encourages the specific microbial communities capable of functioning at near zero temperatures. It extends the effective growing window by warming the soil surface enough, for long enough, to allow short-season crops to complete their cycle. The Sami people of northern Scandinavia developed a farming system that used reindeer as the machinery. Herds were directed across specific landscape areas at specific times of year, not for the reindeer's benefit, but for the land's. The reindeer broke up permafrost surface layers with their hooves, aerating soil that would otherwise remain compacted. Their manure deposited concentrated nitrogen in areas that had been selected for cultivation. The physical disturbance created by a herd moving across the landscape produced microclimatic warming effects, visible to researchers studying the vegetation changes that followed herd movements. The reindeer were not simply animals. They were a managed agricultural implement, guided across the landscape by knowledge of exactly what their presence would produce. The Norse communities of ancient Greenland, established in a period of relative climatic warmth and sustained for several centuries, before their mysterious disappearance, maintained agricultural systems in conditions that modern Greenlandic agriculture has not successfully replicated. Their soil preparation techniques, described partially in Norse sagas and partially in the archaeological record, involved specific combinations of manure application, ground burning, and the cultivation of particular plant species whose root systems broke up and warmed the soil in the manner that modern cover crop research confirms as effective. They knew something about farming frozen ground, and when they were gone, the knowledge went with them. At its peak, the Aztec capital of Tenochtitlan was one of the largest cities on Earth. When Spanish conquistadors first approached it in 1519, they described it in letters home as larger and more magnificent than any city they had seen in Europe, including Seville, which was at that time among the most populous cities on the continent. The population of Tenochtitlan at its height is estimated at somewhere between 200,000 and 300,000 people. It sat in the middle of a lake. It had no hinterland of conventional farmland sufficient to feed it. It was fed from the water itself. The Chinampa system, floating island gardens constructed in the shallow lake beds surrounding the city, produced harvests of a density and frequency that have never been surpassed by any agricultural system at equivalent scale. The islands were built from alternating layers of lake mud and organic material, anchored by willow trees whose root systems grew down through the island structure into the lake floor. Each island was narrow enough that water could reach both long edges, providing continuous moisture access to every plant on the surface. Between the islands, the canals themselves were managed as aquaculture systems, their waters enriched with organic material from the growing surfaces and harvested for fish and aquatic plants. The planting cycle on a chinampa never stopped. While one crop was being harvested at the center of the island, seedlings for the next crop were already established in a nursery section at one end. There was no fallow period, no waiting, no gap in production. The islands produced up to 7 full harvests per year, a yield figure that modern vertical farms, with artificial lighting and climate control, and sophisticated hydroponic systems, are still working to equal. The Aztec Chinampa system was vertical farming, not in the sense of growing upward through multiple stacked floors, but in the sense of using vertical integration to maximize productivity from a constrained horizontal footprint. Every element of the system contributed to every other element. The lake fed the islands fed the lake. The city produced waste that was collected, processed, and returned to the growing system as fertilizer. The entire productive cycle was closed, self-reinforcing, and extraordinarily efficient by any metric applied to it. This model, the integration of multiple productive systems into a single coherent whole, maximizing yield from minimal footprint, is the foundation of what modern urban agriculture, vertical farming, and food systems design are currently attempting to build. Billions of dollars are invested annually in startups, promising to achieve what the Aztec engineers achieved without a single electronic component, powered entirely by the accumulated knowledge of generations of farmers who understood how water, soil, biology, and human labor could be integrated into something greater than any of its parts. The Aztecs called it farming. We call it the future, and we are still catching up to what they knew. 3,000 years ago, in the river valley civilizations of northern India, a text was compiled that modern scholars classify as a work on plant science. The Vrikshaya Veda, the science of plant life, contained within its chapters something that most ancient agricultural texts do not: specific prescriptions for specific problems, not general guidance. Not seasonal advice, targeted treatments, matched to diagnosed conditions, applied in precise quantities and at precise times. One of those treatments was Panchagavya, 5 products derived from the cow milk, curd, ghee, urine, and dung, combined and fermented together for a specific period, then diluted and applied to soil and plant surfaces. The ancient text described outcomes: reduced root disease, improved germination rates, stronger plant growth in the weeks following application. When modern microbiologists analyzed Panchagavya using contemporary laboratory methods, they found a complex community of beneficial bacteria and fungi organisms known to actively suppress the pathogens responsible for soil-borne root diseases, to produce plant growth hormones, and to stimulate immune responses in plant root systems. The ancient farmers had no knowledge of microbiology. They had centuries of empirical observation, passed carefully down through generations, that told them what the mixture did and how to make it. In ancient Rome, the agricultural writer Pliny the Elder documented the practice of applying crushed volcanic rock, specifically the material called pozzolana, found near the volcanic landscape around Puteoli, to agricultural fields. Later, Roman commentators dismissed this practice as superstition, noting that the connection between ground rock and improved harvests was not mechanistically explicable. Modern soil science explains it easily. Volcanic rock dust delivers trace minerals, silicon, calcium, iron, magnesium, in forms that soil microorganisms can process and that plant roots can absorb. It also modifies soil pH in ways that suppress specific fungal pathogens. Pliny was not recording superstition. He was recording an empirically validated agricultural practice that modern organic farming is currently reviving under the name rock dust amendment. Ancient Chinese agricultural records from the Han Dynasty describe sulfur fumigation of stored grain and seed stocks before planting, a practice applied specifically to prevent fungal contamination. The chemical mechanism elemental sulfur's antifungal properties was not understood by the people applying it. The outcome was. And the outcome they were managing is the same outcome that modern sulfur-based fungicides address through a chemically identical mechanism. What connects these examples across cultures and centuries is not that ancient farmers were working from a shared theory. They had no shared theory. What they shared was a method, the method of observation, of trial across generations, of preserving what worked and discarding what did not. That method, applied consistently across centuries, produced a pharmacopoeia of agricultural treatments whose effectiveness modern laboratory analysis continues to confirm, case by case, with a regularity that has stopped surprising the researchers doing the analysis. For at least 3,000 years, the Haudenosaunee, the people known in English as the Iroquois, have planted three crops together: corn, beans, and squash, always together, always in a specific spatial arrangement, always following a planting sequence in which the corn is established first, then the beans are introduced around the corn's base, then the squash is seeded in the spaces between. The system has ceremonial significance within Haudenosaunee culture. The three crops are honored as living sisters, inseparable and mutually sustaining. But the ceremony reflects a biological reality that took Western agricultural science until the 1980s to formally document. The corn provides the physical structure, a vertical axis around which the bean vines can climb without requiring any external support. The beans' legumes host bacteria on their root nodules that extract nitrogen from the atmosphere and deposit it in the soil in forms that the corn and squash root systems can absorb directly. The squash, with its broad, rough-surfaced leaves, spreads across the ground between the corn stalks, shading the soil to suppress weed germination, reducing soil surface temperature during the heat of the day, and retaining moisture that would otherwise evaporate in the summer sun. But the relationship between the three sisters goes deeper than what is visible above the ground. When researchers began examining the root systems and the soil biology of Three Sisters plots, they found what mycologists had only recently learned: to look for mycorrhizal networks connecting all three plant species in a mutual exchange system. Nutrients produced in surplus by one species moved through the fungal network to the species that needed them. The biological community in a Three Sisters field was not three species growing in proximity. It was one integrated system. And the combined yield? When researchers calculated the total caloric production of a Three Sisters planting versus the same area planted in monoculture crops of each species separately, the Three Sisters system produced more food per acre than any of its components grown alone. The ancient farmers had not discovered companion planting by accident. They had refined, across 3,000 years of cultivation, a food production system that was more efficient than any of its parts. The Ethiopian shamba, a traditional garden style that integrates over 40 plant species in a single cultivated plot, applies the same underlying principle at greater complexity. Each species has been selected for its compatibility with the others. The combinations suppress specific pests, create specific microclimates, and provide the soil biological community with the diversity of inputs it needs to remain active and fertile. The apparent chaos of a shamba garden, which looks, to an eye trained on European field agriculture, like an overgrown tangle, is in fact a highly organized biological system whose organization operates at a level of complexity that requires generations to learn to read. There is a practice in traditional German and Eastern European farming that was documented by agricultural historians before it disappeared from widespread use and dismissed, for generations, as a primitive misunderstanding of how soil worked. Farmers would gather wood, bury it in prepared trenches in their fields, and then carefully, through a process of controlled combustion that required considerable skill to manage correctly, partially burn the buried material without fully consuming it. The resulting mounds were raised above the field surface by the volume of buried wood. They were called Hugelkultur beds. The partially charred wood beneath the soil surface would, over years and decades, slowly decompose into a structure that held water, stored nutrients, and hosted microbial communities of unusual density. The modern name for what the wood becomes through this process is biochar, and it is now one of the most actively researched soil amendments in regenerative agriculture, for precisely the reasons that the German farmers who developed it over centuries understood empirically. It persists in the soil indefinitely. It creates physical habitat for beneficial microorganisms. It increases the soil's capacity to hold water, and it sequesters carbon in a form stable enough to remain in the ground for centuries. Traditional Japanese farming culture developed a parallel practice using bamboo and rice straw. The material was charred under controlled conditions, a process requiring the specific management of oxygen and heat that the farmers learned through experience, passed between generations, and worked into paddy fields before planting. The improvement in plant growth and disease resistance that followed the application was documented across generations of farmers without any understanding of the mechanism. The mechanism, as modern biochemistry now confirms, involves the colonization of the biochar's porous structure by soil, bacteria, and fungi in communities far more diverse than those found in the surrounding unconditioned soil. The fermentation strand of ancient soil building produced a different set of discoveries. In traditional Korean farming practice, a technique now called Korean natural farming involves the preparation of fermented plant extracts materials gathered from specific wild plants, packed into clay vessels with specific supplementary ingredients, and left to ferment for defined periods before the liquid is diluted and applied to growing plants and soil. When researchers submitted samples of these traditional ferments for biochemical analysis, they found a range of compounds not typically considered in the context of agricultural inputs. Auxins and cytokinins, plant growth hormones produced during the fermentation process by the microbial community acting on the plant material. These hormones, when applied to root systems, directly stimulate cell division, root extension, and the plant's own immune signaling. The Korean farmers who developed this practice 2,000 years ago had no concept of plant hormones. They had observed, generation after generation, that their crops grew stronger and with greater resistance to disease after the application. They had preserved the practice because it worked. Modern biochemistry has now explained precisely why. Across the ancient world, almost without exception, farmers organized their planting calendars around the sky. The Babylonians maintained agricultural almanacs that scheduled sowing and harvest dates according to lunar phases, planetary positions, and the rising and setting of specific star groups. The Romans followed lunar planting calendars that governed when particular crops should be sown, pruned, and harvested. Celtic farming communities across northern Europe organized their agricultural year around the observation of star positions at dawn and dusk. In the Andes, the Inca aligned planting schedules with the disappearance and reappearance of the Pleiades on the horizon, a celestial calendar precise enough to account for year-to-year variation in the appearance date and adjust agricultural timing accordingly. These practices are distributed across cultures with no documented contact with each other. They describe the same fundamental relationship between celestial cycles and agricultural decisions in different languages, with different specific markers, but with a consistency that raises a question that pure cultural diffusion cannot answer. Why did virtually every agricultural civilization on Earth, independently, arrive at the same conclusion? The modern study of lunar planting calendars is not settled science. Research conducted by the Forschungsinstitut für biologischen Landbau, the Swiss Research Institute for Organic Farming, has produced studies across more than a decade that show measurable differences in germination rates, disease resistance, and crop quality between plantings timed to specific lunar phases and those conducted without reference to lunar timing. Some of those differences reach statistical significance, others do not. The results are consistent enough to sustain the research program, and inconsistent enough to resist a simple conclusion. But the most interesting question may not be whether lunar timing works. It may be what the practice of lunar observation required the farmers to develop in order to practice it. Accurate astronomical observation across multiple years, sufficient to establish reliable baseline patterns. Record-keeping sophisticated enough to maintain those records across generations. The mathematical capacity to predict celestial events in advance and adjust planting schedules accordingly. A community organization sophisticated enough to coordinate planting timing across multiple farms in response to shared astronomical data. In other words, the practice of lunar farming required, as its prerequisite, a level of scientific infrastructure and community organization that Western history has rarely credited to the agricultural societies that practiced it. Whether or not the moon itself directly affected plant growth, the observation of the moon produced farming communities that were scientifically literate, organizationally coherent, and in possession of long-term empirical records about how their particular crops performed under particular conditions. That knowledge base was an extraordinary agricultural tool, and it disappeared, largely, when the cultures that developed it were displaced, converted, or absorbed by civilizations that kept different calendars and did not inherit the observational tradition that the old ones had spent centuries building. Fly over the right parts of the British Isles in the right season, when the light falls at a low angle across the landscape, and shadows exaggerate the subtle rises and depressions in the earth, and you will see them. Ancient field boundaries, not the straight lines of modern agricultural division, imposed by property law and the logic of machinery. Curves, spirals, arcs that follow the natural contour of the land rather than overriding it. The remnants of a way of organizing growing space that predates the Roman arrival in Britain and persists as ghost marks in the grass long after the people who designed it are gone. Modern industrial agriculture organizes fields in rectangles because rectangles are efficient for machines. A combine harvester, a tractor pulling a plow, a pesticide sprayer, all of these move most efficiently across flat, rectangular surfaces with right-angle turns at the headlands. The geometry of industrial farming is the geometry of mechanical convenience. It has nothing to do with the land itself. Ancient farming geometries arose from entirely different logic. There were no machines to accommodate. There was only the land, its slopes, its drainage patterns, its wind exposure, its frost pockets, its dry ridges, and its wet hollows, and the knowledge accumulated by farmers who walked every meter of their fields every season for generations of what those properties meant for the crops planted within them. Aerial survey and satellite imaging of ancient agricultural landscapes have revealed a diversity of field geometries that modern agriculture has entirely eliminated. Spiral arrangements in Celtic field systems of the British Isles, radial patterns in pre-Columbian clearings across the Amazon basin, concentric ring garden designs in traditional Korean cultivation, the precise north-south orientation grids of Roman centuriation that organized farmland across North Africa and the Middle East, the hexagonal tessellation of traditional Moroccan argan orchards, each tree positioned at the vertex of a hexagonal grid that maximizes canopy coverage while minimizing competition for root space. The emerging discipline of landscape ethnobotany, the study of how human cultures organize plants in physical space, has begun finding evidence that these geometric choices were not arbitrary, not aesthetic, not merely traditional. Each geometry creates specific microclimatic conditions within the planted space. Spiral arrangements modify wind flow in ways that reduce moisture loss from exposed soil. Radial patterns create edge zones, boundaries between open and cultivated space that concentrate the biological activity of beneficial insects. Concentric ring designs produce a graduated moisture gradient that allows a single plot to support multiple crop species with different water requirements simultaneously. The ancient farmers who chose these shapes may not have described what they were doing in terms that modern ecology would recognize. But they observed, season after season and generation after generation, that certain shapes worked, that the field organized one way produced differently from the field organized another way. And the shapes they chose, once examined through the tools of modern landscape ecology, turn out to have been correct. In the lowland savannas of what is now Bolivia, in a region called the Llanos de Mojos, there are earthworks, not small ones, not the kind that announce themselves dramatically on first encounter. From the ground, they look like gentle ridges, slightly elevated above the surrounding land, separated by channels that fill with water during the rainy season and retain moisture long into the dry months that follow. They look natural. They look like the landscape shaped itself this way over time, through some geological process unrelated to human intervention. From the air, the true scale becomes visible. The ridges are not random. They are organized across hundreds of thousands of hectares in a pattern too deliberate, too consistent, too geometrically precise to be anything other than intentional. Raised agricultural fields, separated by water channels, extending across an area larger than the Netherlands, created by human hands between roughly 1,000 and 2,000 years ago. The engineering principle is elegant in its completeness. During the rainy season, the Llanos de Mojos floods. Water covers the savanna to depths that make conventional surface agriculture impossible. But the raised fields sit above the floodwater, their growing surfaces elevated by the earth, excavated to create the channels that run between them. During flooding, the channels fill with water, fish move into them from the surrounding landscape, and the aquatic ecosystem of the channels begins producing its own biological resources. When the dry season comes and the water retreats, the channel mud is dredged and applied to the raised field, surfaces the most nutrient-rich, biologically active material available, delivered directly from an aquatic system that has been processing organic matter continuously through the wet months. The fields receive their amendment. The channels are deepened and cleaned. The cycle prepares itself to begin again. The fish in the channels fertilize the water with their waste. The water fertilizes the fields. The organic material from the fields feeds the fish. The system is a closed nutrient loop, a biological machine that produces food while simultaneously regenerating the fertility of the surfaces on which the food is grown. Modern agricultural system designers call this circular agriculture. The people of the Llanos de Mojos were practicing it at continental scale more than 1,000 years ago. When European explorers arrived and passed through this landscape, they recorded it as empty jungle, uninhabited, a wilderness. They were walking through an abandoned garden the size of a small country, its geometry still visible, its channels still holding water in their ancient courses, its raised surfaces still elevated above the floodline by earthworks that had not been maintained for centuries and had not yet fully eroded. They did not know what they were looking at, and so they described it as nothing. On the island of Bali, the cultivation of rice has been organized for at least 1,000 years by a network of water temples. The temples are not merely religious sites. They are nodes in an irrigation management system that coordinates water distribution, planting schedules, and harvest timing across entire watersheds. The priests who manage the temples are not only spiritual custodians, they are the operators of what modern systems theorists would recognize as a distributed information network, a system that aggregates local observations about water availability, pest pressure, and crop readiness from across an entire landscape, and uses that aggregated information to make decisions that individual farmers, acting alone, could not make as effectively. For most of the 20th century, anthropologists and development planners described the Balinese water temple system as a religious tradition, culturally significant, worthy of respect, but not technically functional in any way that modern irrigation management should need to account for. This assessment drove the agricultural development policies applied to Bali during the Green Revolution period, when traditional temple-coordinated planting schedules were disrupted in favor of continuous planting cycles designed to maximize annual yield. The result was a collapse in rice harvests across significant portions of the island. Pest populations that the temple system's synchronized fallow periods had been suppressing exploded across the landscape. The rice water weevil, whose populations the traditional planting calendar had managed by creating landscape-level breaks in its food supply, found a continuous food source and thrived. Ecologist J. Stephen Lansing spent years studying the Balinese water temple system in the 1980s. What he found reframed the entire story. The temple planting calendar was not primarily a religious ritual. It was a pest management algorithm, a system that coordinated planting timing across the entire watershed so that synchronized fallow periods created gaps in pest population food availability at the landscape level. No individual farmer's decision could create a sufficiently large gap. The gap required coordination across hundreds of farms. The water temple provided that coordination, embedded within a ceremonial framework that ensured compliance across generations. The ceremony was the delivery mechanism for an ecologically sophisticated decision. The decision was real, and it worked. The ceremony was the form in which a practical agricultural truth had been preserved across 1,000 years of changing politics, changing rulers, and changing development fashions. When the ceremony was dismissed as non-functional tradition, the practical agricultural truth it carried was dismissed along with it. The landscape paid the price. What the Balinese farmers had done, with their mandala-shaped temple gardens and their ceremonially coordinated planting schedules, was encode a complex systems management protocol into a form that every member of their community could participate in and sustain. It required no technical education. It required only the shared understanding that the ceremony was necessary, a belief that had been preserved, uninterrupted, for 1,000 years, because it was. In 2022, researchers at the University of Western Australia published findings from a study in which wheat seeds were exposed to specific acoustic frequencies before planting. The seeds treated with frequencies in a particular range showed germination rates significantly higher than the control group, and the plants that emerged from them developed root systems measurably larger and more extensive than those from untreated seeds. The same year, a team at Seoul National University documented changes in stomatal aperture, the pores through which plants exchange gases and regulate water in response to specific sound frequencies applied to leaf surfaces. The plants were responding to vibration in ways that had direct consequences for their growth, their water management, and their disease resistance. These findings were described, in the coverage they received, as surprising. In the ancient Sanskrit texts that describe traditional Indian agricultural practice, there are passages prescribing the singing of specific melodic patterns in fields during critical growth phases at germination, at flowering, at the point of grain formation. The prescribed patterns are specific enough that they can be transcribed into musical notation and identified as particular ragas, classical Indian musical forms associated with specific times of day. Some of those ragas are also prescribed, within the broader classical tradition, for performance at dawn and dusk, the same transition hours when the texts prescribe musical engagement with crops. In traditional Mayan agricultural ceremony, specific drumming patterns accompanied the planting of seed corn rhythmic patterns, prescribed by ceremonial tradition for specific planting occasions rather than others. The ceremonies were understood, within the tradition, as communication with the spiritual forces governing growth. They were also, in their specific physical properties, the application of vibrational energy to seed material at the moment of planting. The connection between these ancient practices and the modern acoustic biology research is not a simple causal argument. The ancient farmers were not intentional acoustic biologists working from an understanding of plant physiology. They were practitioners of traditions that had been refined over generations of observation, in which the specific practices that produced better outcomes had been preserved, and the practices that produced no effect had been gradually abandoned. Whether the acoustic dimension of those practices was causally significant, whether the singing and the drumming actually influenced plant biology in ways consistent with modern acoustic research, remains scientifically uncertain. The research is real, the mechanisms are real. The connection to ancient practice is suggestive rather than proven. But the more fundamental observation holds regardless of how that question is eventually resolved. Across the ancient agricultural world, a relationship between sound, timing, and growing practice was identified and maintained with enough consistency to suggest that the people observing it were observing something. What exactly they were observing, and how much of it has a mechanistic basis that modern science has not yet fully mapped, is a question that researchers are, quietly, beginning to take seriously. As they should. Around 1200 BCE, something catastrophic happened across the eastern Mediterranean. The Mycenaean civilization of Greece collapsed. The Hittite Empire in Anatolia collapsed. Several major Canaanite city-states collapsed. The Egyptian New Kingdom survived, but barely its records from this period describe foreign invasions, drought, and famine in language that carries the unmistakable quality of a civilization writing about its own near death. Historians call it the Bronze Age collapse, and it remains one of the most studied civilizational catastrophes in history. The causes are debated. Drought, invasion, internal revolt, systems failure, some combination of all of these. The debate continues because no single cause seems adequate to explain the simultaneity and scale of the collapse across an entire region. But the agricultural record offers a dimension of this story that the political and military histories rarely emphasize. In lake sediment cores from across the eastern Mediterranean, drawn from ancient lake beds that have been preserving environmental records in their layers for thousands of years, there is a consistent signature. Beginning approximately 2 to 3 generations before the major collapse events, the sediment layers show a spike in erosion particles, soil washing off agricultural land and depositing in lakes. Pollen samples from the same cores show the decline of cultivated plant species and the increase of pioneer species. The weedy, opportunistic plants that colonized disturbed or exhausted land. The agricultural systems of the Eastern Mediterranean Bronze Age were failing before the political systems collapsed. The soil was washing off the hillsides. The crop diversity was shrinking. The harvests were declining year by year, at a rate slow enough that no single season could be identified as the breaking point, but fast enough that, across a generation, the cumulative effect was a food production capacity no longer sufficient to sustain the population that had grown to depend on it. The political collapse, the invasions, the revolts, the abandoned cities followed the agricultural collapse by approximately 20 to 30 years. The palaces fell after the harvests did. The armies stopped being paid after the grain stopped arriving. The empires contracted to what the exhausted land could support, and what it could support was not enough to sustain what had been built on top of it. This pattern agricultural degradation, preceding and precipitating political collapse, has been documented across multiple civilizations, in multiple periods, on multiple continents. It is not the most commonly taught interpretation of civilizational collapse, which tends to focus on the dramatic terminal events, the battle, the invasion, the plague, the drought. Those events are real, and their roles are real. But beneath almost all of them, in the agricultural record that sediment cores and pollen samples and ancient grain storage records make visible, the farms were already in trouble before the kingdoms noticed. The collapse begins in the field. It always has. At the height of the classic Maya period, roughly 250 to 900 CE, the civilization maintained one of the most sophisticated agricultural systems on the planet. The lowland Maya cultivated raised fields in the wetland margins of river systems, using the same integrated water-field aquaculture principles that the Llanos de Mojos people were developing independently to the south. In the highlands, they built terraced hillside systems with engineering precision that the Andean civilizations were demonstrating on the other side of the continent. Between the wetlands and the highlands, in the forest zones that covered most of Maya territory, they managed forest gardens, multi-layered, productive landscapes that integrated food, trees, medicinal plants, fiber crops, and nitrogen-fixing species in combinations calibrated to produce food while maintaining the biological integrity of the forest system. They also maintained knowledge. The Maya codices, the bark paper books that encoded centuries of astronomical observation, agricultural calendar management, soil classification systems, and crop variety records represented a library of agricultural intelligence assembled across generations with the care that their civilization invested in all things. The calendar system that modern popular culture has reduced to a 2012 apocalypse meme was, in its agricultural application, a precision instrument for managing planting, pest management, and harvest timing across a complex, multi-system agricultural landscape. The collapse of this civilization is a story told through many lenses. The drought evidence is real. Paleoclimatological data confirms that the terminal classic period, between roughly 800 and 1000 CE, was accompanied by extended drought events severe enough to stress any agricultural system. But the sediment record in Lake Chichancanab, in the Yucatan, adds a dimension to the collapse story that drought alone cannot account for. Beginning approximately 150 years before the major city abandonments of the terminal classic period, the lake sediments show a sharp and accelerating increase in erosion load. Soil was leaving the agricultural hillsides at rates that had not been seen in the preceding centuries of Maya civilization. The erosion was the consequence of a specific agricultural choice. As the classic Maya population grew, and it grew substantially, to densities that some researchers estimate were higher than any tropical American civilization, before or since the demand for food production increased. Meeting that demand required expanding cultivation. The forest gardens and raised fields, which were extraordinarily productive, but also extraordinarily labor-intensive, could not be expanded quickly enough. Hillside clearing and slope cultivation was faster. It was also, without the terracing infrastructure that the highland Maya had built, but that the lowland Maya had not consistently applied, rapidly destructive of the thin soils that the tropical environment had spent centuries accumulating. The soil washed away, not dramatically, not in a single catastrophic event. Season by season, rainfall by rainfall, the hillside cultivation that had replaced the forest gardens and raised fields exported the agricultural heritage of the Maya lowlands into the lakes and rivers below. The harvests declined. The population that had grown to depend on those harvests could not be sustained. And when the droughts came severe enough to be challenging for any agricultural system, fatal for one that had been silently weakened for a century and a half, the civilization that had built pyramids and developed the most sophisticated astronomical calendar in the pre-Columbian Americas did not have enough food, left in its reserves to outlast the crisis. The temples kept going up, right to the end. The kings kept waging their ritual wars, and beneath the cities, the soil had already surrendered. The oldest agricultural records in human history are written in clay. Cuneiform tablets from the Sumerian city-states of ancient Mesopotamia, preserved in the dry conditions of what is now southern Iraq for 4,000 years, contain yield data. Careful, consistent records of how much grain specific fields produced in specific seasons. Records kept by administrators managing grain stores, by temple officials tracking tithes, by merchants calculating what they could expect from the harvest. When researchers plotted the yield figures from those tablets on a graph, the resulting curve was unmistakable. From approximately 2400 BCE to 1700 BCE, a period of 700 years, the documented wheat yields in Sumerian agricultural records declined steadily, consistently, without reversal. The decline was not dramatic in any single year. It was the kind of decline that each generation experienced as merely continuing the trend they had been born into. Too gradual to constitute an emergency, too relentless to be a temporary setback. By the end of this 700-year decline, wheat production in many Sumerian city-states had fallen by 65% from its peak. The administrative records note, with the matter-of-fact tone of bureaucratic documentation, that certain fields were being converted to barley, a crop more salt-tolerant than wheat, capable of producing some yield from soils that wheat could no longer tolerate. The salts were the cause. The river water used to irrigate Mesopotamian fields carried dissolved minerals that evaporated from the soil surface, leaving behind a residue that accumulated season by season, year by year, decade by decade. The Sumerian agricultural records describe the problem with striking specificity. The phrase used in multiple tablets translated as "the earth turning white" refers to the visible salt crust forming on the surface of formerly productive fields. The white earth could not grow wheat. With time, managed only by the progressive shift to more salt-tolerant crops, it would not grow barley either. The civilization that invented writing used that writing to document its own agricultural collapse across 7 centuries. They recorded the declining yields. They recorded the spreading white earth. They recorded the administrative decisions to shift crops, to abandon fields, to consolidate populations toward the areas where the soil could still produce. And they could not stop what they were recording, because the knowledge of how to stop it, the drainage systems, the soil flushing techniques, the crop rotation practices that would have given the salt-degraded land time to recover, had not been developed, or had not been applied at sufficient scale, or had been applied and failed against the fundamental unsustainability of irrigating flat, arid land without adequate drainage. This is the world's first documented soil crisis, 4,000 years old, produced by a civilization intelligent enough to write about it and not powerful enough to reverse it. The soil of modern Mesopotamia of southern Iraq still bears the marks. Large areas that were once the most productive farmland in the ancient world are currently salt flats. The record that the Sumerians kept in clay is visible in the earth itself. The Maya, the Sumerians, the Bronze Age Mediterranean civilizations, the Nabatean desert kingdom that the Romans could not sustain, the Norse Greenland settlements that farmed impossible ground for 3 centuries before vanishing. The pattern that connects them is not drought, it is not war. It is not plague or invasion or political failure, though all of those appear in the terminal chapters of each story. The pattern is this: population grows, agricultural intensification follows. The knowledge-intensive, soil-sustaining practices developed over generations are replaced, gradually, with simpler approaches that produce more food per unit of labor in the short term. The simplified system begins degrading the foundation. It depends on the soil, the water system, the biological network that makes the land productive at a rate slow enough that no single season registers as a crisis. A generation passes, and the degradation continues. Another generation. The agricultural capacity of the landscape quietly diminishes, while the civilization built on top of it continues expanding, consuming, and building, unaware that the floor beneath it is thinning. Then, something external arrives. A drought, an invasion, a disease, a political disruption of the maintenance workers who keep the water channels flowing. Under normal conditions, under the conditions that existed at the height of the civilization's agricultural competence, The external shock would have been a setback, painful and costly, but recoverable. The food reserves would have buffered the shortage. The agricultural systems would have produced enough, even in reduced conditions, to sustain the population through the crisis. But the reserves are not what they were. The agricultural systems are not what they were. The knowledge of how to maintain them has thinned along with the soil, as the people who held it were displaced, as the practices they embodied were set aside in favor of the simpler approaches that produced more food with less knowledge in the short term. The civilization that thought itself strong discovers, in the moment that the external shock arrives, that it has been hollow for a generation. The specific modern numbers sit alongside this pattern without requiring editorial comment. 1/3 of global agricultural land currently degraded. Topsoil loss outpacing formation by a factor of 10 to 40, depending on region and farming practice. Groundwater aquifers being depleted at rates that geological recharge cannot approach. A global food system dependent on 3 crop species for more than half of human caloric intake. The pattern is known. It has been documented across multiple civilizations, multiple continents, multiple millennia. The question is not whether it is recognizable. The question is whether we are already inside it. In the middle of the 18th century, something began to shift in the way that Western civilization understood knowledge itself. The scientific revolution had established the principle that valid knowledge was knowledge produced through formal, reproducible, documented investigation, tested by experiment, verified by peer confirmation, and recorded in institutional archives. This principle was, in its application to natural science, genuinely transformative. It produced extraordinary advances in physics, chemistry, and medicine across the following centuries. Applied to agriculture, however, it had an unintended consequence that has never been fully accounted for. The knowledge that traditional farming communities possessed accumulated over generations of empirical observation, refined through centuries of trial, preserved in practice rather than on paper, did not meet the formal criteria of scientific validity. It was oral, it was behavioral. It was embedded in the seasonal rhythms of communities whose members had been farming the same land for centuries and whose understanding of that land was inseparable from the physical act of farming it. The Industrial Revolution did not set out to destroy this knowledge. It set out to improve agricultural productivity, to feed the growing urban populations that industrialization was creating, and to apply the same principles of efficiency and systematization to farming that were transforming manufacturing. The results, in the narrow terms that industrialization measured output per unit of labor, were impressive. Fewer farmers were needed to produce more food. The land freed from traditional smallholder cultivation could be reorganized into larger, more efficiently managed units. The knowledge required to farm traditionally complex, local, deeply contextual, could be replaced by knowledge that was simpler, more transferable, and more compatible with the industrial model. Between 1750 and 1850, the enclosure of the English Commons displaced approximately 1.5 million people from the agricultural landscapes where their families had practiced traditional farming for centuries. The Commons shared land, managed collectively, according to traditional protocols that maintained soil health, water availability, and biodiversity, were divided, fenced, and privatized. The families who had managed them were offered the choice between wage labor on the enclosed estates or migration to the industrial cities growing up around the new factories. Most moved to the cities. They brought their knowledge with them. Their children, growing up in urban environments with no access to land and no context for the agricultural practices their parents had embodied, did not inherit it in functional form. Within 2 generations, the knowledge that had sustained English agricultural communities for centuries existed only in the memories of people who were no longer farming, and then it did not exist at all. No book was burned. No decree was issued ordering the destruction of traditional agricultural knowledge. The knowledge simply lost the conditions it needed to survive. It was oral and behavioral and local. It could not be preserved in a library or transmitted by correspondence. It required land, community, and practice to remain alive. When those conditions were destroyed by economic forces that had no particular interest in what they were losing, the knowledge died the way a language dies not in a single catastrophic moment, but in the gradual disappearance of the last people who spoke it fluently enough to teach it. In the autumn of 1970, Norman Borlaug stood in Stockholm to accept the Nobel Peace Prize. The citation described his work as having contributed more to the welfare of humanity than any other living person. This was not a hyperbolic assessment by the standards of what Borlaug had accomplished. His development of high-yield, disease-resistant wheat varieties, combined with the irrigation infrastructure and synthetic fertilizer programs that accompanied their deployment, had produced harvest increases of 300 to 500% in the space of a decade in South Asia and Latin America. The demographic projections that had predicted catastrophic famine across those regions did not materialize. Hundreds of millions of people ate who, by the most credible models available, should not have been able to. The achievement was real. The gratitude was earned. And the bargain at the center of the achievement was real too, though it was not described in those terms in Stockholm. The high-yield varieties that Borlaug developed were engineered for performance under specific conditions. Heavy synthetic nitrogen application, consistent irrigation, and pesticide use to manage the pest pressure that the simplified genetics of uniform crops naturally attracted. Without those inputs, the high-yield varieties did not significantly outperform the traditional varieties they were designed to replace. With them, the yield differences were dramatic. The varieties were not simply better crops. They were better crops within a specific technological package, and the package was inseparable from the crop. International development organizations understood this. The Rockefeller Foundation, the Ford Foundation, and subsequently, the World Bank deployed the Green Revolution package across developing world agricultural regions with a consistency that reflected deliberate policy rather than simple market adoption. Financial support for agricultural development loans, subsidized input programs, technical assistance was structured to favor farmers who adopted the approved varieties and the input package that made them perform. Farmers who maintained traditional varieties found themselves excluded from the loan programs that increasingly determined whether farming was economically viable in the modern world. Internal documents from the principal foundations involved, some now available through academic archives, reveal that the replacement of traditional crop varieties was not viewed as unfortunate collateral damage, but as a policy objective. The language used in those documents speaks of modernization, of progressive replacement, of eliminating backward practices. The intention, in the minds of the people writing these memos, was humanitarian. The practice they were eliminating was the maintenance of thousands of years of locally adapted crop diversity. Within 2 decades of the Green Revolution's most intensive deployment period, the 1960s and 1970s, the agricultural landscapes of the Punjab in India, the Irrawaddy Delta in Burma, the Central Highlands of Mexico, and many other regions that had supported extraordinary crop diversity had been substantially converted to monocultures of approved high-yield varieties. The traditional varieties that had sustained those regions for millennia adapted to local soils, local pest pressures, local rainfall patterns, local culinary traditions had no market. Without market demand, farmers could not afford to grow them. Most were never formally collected by any seed bank. They simply ceased to exist. The year 2000 arrived. The FAO completed its assessment of what had happened to global crop genetic diversity across the preceding century. 75% gone. Permanently. The people who had facilitated the largest single act of biological erasure in agricultural history had, in many cases, received international recognition for their contributions to human welfare. They believed those contributions were real. Most of them were. The cost of those contributions was not included in the accounting. On a July morning in 1562, in the central plaza of the Yucatan city of Mani, a Spanish bishop named Diego de Landa presided over an auto de fe. The objects being burned that day were not people. They were books, the bark paper codices of the Maya civilization, which de Landa had ordered confiscated from the communities under his authority. In his own account, written afterward, de Landa described the books as containing nothing but superstition and falsehoods, and expressed satisfaction at having deprived the native population of texts that reinforced their adherence to practices he regarded as incompatible with Christian civilization. Scholars estimate that hundreds of Maya books existed at the time of the Spanish conquest. 4 survive. The 4 that remain held today in museums in Dresden, Madrid, Paris, and Mexico City contain astronomical tables, divinatory calendars, and mythological narratives. Among the ashes of the books that did not survive were agricultural almanacs, planting calendars that encoded centuries of empirical observation about which crops, in which combinations, planted at which times, produced what results in the specific microclimates of the Yucatan Peninsula. Soil classification systems that the Maya had developed to distinguish the different growing properties of the region's complex mosaic of soil types. Variety records cataloging the specific seed stocks maintained by different communities for different growing conditions. De Landa was not the first. In 48 BCE, when Julius Caesar's forces set fire to ships in the harbour of Alexandria, the flames spread to the warehouses along the docks and then to the Great Library. The scale of what burned that day, and in the subsequent fires that damaged the library further across the following centuries, cannot be precisely calculated. But ancient catalogues suggest that among the collection's holdings were agricultural texts from Egypt, Babylon, Persia, and India, representing accumulated farming knowledge from civilizations stretching back 3,000 years before the library's founding. The knowledge of how specific crops had been grown in specific landscapes across the ancient world existed in those books and nowhere else. It did not survive. In British India, the colonial administration's approach to traditional agricultural knowledge was less dramatic than fire, but equally effective across a longer timeline. The land settlement systems imposed across large portions of the subcontinent in the 19th century converted subsistence food crop farmers to export cash crop producers, indigo, opium, and cotton on fields that had previously grown the diverse food crops that sustained local populations. The traditional soil management practices associated with diverse cropping systems were incompatible with the monoculture requirements of export crop production. Farmers who were forced to shift crops did not simply change what they planted. They lost the context within which their soil management knowledge had been practiced. The knowledge became inapplicable, and inapplicable knowledge across a generation becomes forgotten knowledge. The agricultural texts of ancient Egypt, of Babylon, of the Maya, of the Indian subcontinent. Each loss is a specific event with a specific cause. Together they constitute something larger, the systematic removal, over centuries and across continents, of the written and material record of how human beings had learned to grow food. What could not be burned was often delegitimized. What could not be delegitimized was simply allowed to become economically unviable and then to disappear. When British colonial administrators arrived in the upland regions of Southeast Asia in the 19th century, they observed a farming practice that they described in their official reports as wasteful, destructive, and evidence of agricultural primitivism. The practice was swidden cultivation, sometimes called slash-and-burn farming, though the term obscures more than it reveals. Farmers would clear a section of forest, burn the cleared material to release its nutrients into the soil, farm the cleared land for 2 or 3 seasons, and then allow it to regenerate as forest for 10 to 20 years before clearing and farming it again. The colonial observers saw the burning and the apparent abandonment and concluded that they were witnessing a people who did not understand how to farm. What they were witnessing was one of the most sophisticated long-term agricultural management systems ever developed for tropical forest environments. The fallow period was not abandonment. It was the regenerative phase of a rotation cycle in which the forest's own biological processes, the gradual accumulation of organic matter, the recovery of the mycorrhizal network, the restoration of the soil moisture-holding capacity were doing the agricultural work. The farmers were not farming during the fallow period in the conventional sense. They were managing a biological machine that was producing the conditions for the next growing phase. Modern ecological research has established that traditional swidden agriculture, practiced at appropriate scale with appropriate rotation lengths, maintains soil fertility indefinitely. It produces yields comparable to permanent cultivation. It supports biodiversity at levels that monoculture systems cannot approach. It does not require synthetic inputs. It does not degrade the landscape it operates within. It is, by almost every ecological metric applied to it, superior to the permanent cultivation systems that colonial administrations imposed to replace it. The colonial imposition of permanent cultivation destroyed the fallow cycle. Without the fallow, the soils that had been sustained by the rotation began to degrade within years. The farmers who had been managing those soils for centuries, under a system that required sophisticated knowledge of forest ecology, successional dynamics, and long-term soil cycles, were now farming differently in ways their knowledge had not been designed to sustain. Within 2 generations, the soil was damaged. Within 3, the damage was described in colonial reports as evidence that the traditional population had always been poor farmers. The same pattern played out across Africa, across the Pacific, across the Americas. The Zai pit system of the Sahel, a dryland water harvesting technique that has been documented as one of the most effective dry season food production methods known, was dismissed as primitive ditch digging by colonial agricultural officers who did not recognize what the pits were designed to do. Traditional Polynesian marine agriculture, which integrated reef management with terrestrial food production in a system whose complexity took modern ecologists decades to map, was described as simple fishing by administrators who saw only the harvest and not the management system that made it possible. In each case, the same mechanism was applied. The knowledge was declared illegitimate. The people who held it were told that their practices were backward and that the future required different methods. And when the different methods failed, as they consistently did, in landscapes where they had not been developed and to which they were not adapted, the failure was attributed to the land, not to the replacement system. In 1995, a soil scientist working in the Brazilian Amazon sent a soil sample to a laboratory. The results came back, indicating a level of biological activity and carbon content that did not match the surrounding landscape, not by a small margin, but by orders of magnitude. He sent another sample from a different location nearby. Same result. He looked more carefully at where the samples had been collected. He was standing in the middle of a terra preta patch that stretched for hectares in every direction, and he had been walking through it for months without recognizing what it was. That recognition, that moment when an anomaly in the data becomes a discovery, is where the second half of the story begins. Not with institutions or policy programs or funding allocations, but with individual researchers who followed an anomaly into territory that their field had not prepared them to explore. William Woods spent decades documenting the distribution and properties of terra preta across the Amazon basin, building the scientific case for biochar as a soil amendment from an archaeological discovery that the conventional narrative of tropical agriculture had no framework to accommodate. Clark Erickson's aerial survey work in the Bolivian Amazon brought the raised field agricultural systems of the Llanos de Mojos to academic prominence, transforming what had been catalogued as undifferentiated savanna earthworks into the largest documented ancient agricultural landscape in the Western Hemisphere. J. Stephen Lansing's fieldwork in Bali dismantled decades of development policy assumptions about indigenous irrigation management and established the Balinese water temple system as one of the most sophisticated examples of decentralized ecological management ever documented. Vandana Shiva's work in India, beginning in physics and moving through her direct observation of the Green Revolution's impact on traditional farming communities in the Punjab, produced a body of documentation that gave the global food sovereignty movement its foundational analysis of what the Green Revolution's seed variety replacement had actually cost. Each of these researchers arrived at their subjects through a different disciplinary door and found, on the other side of it, the same thing: that the practices dismissed as primitive were sophisticated, that the knowledge classified as superstition was empirically derived, and that the losses accumulated across a century of agricultural modernization were both larger and more consequential than the mainstream narrative of progress had accounted for. The detective, in each case, was not looking for what they found. They were following something that did not fit a soil that was too fertile, a water system that worked too well, a pest management outcome that required a different explanation. And what they found, when they followed the anomaly far enough, was the shadow of something that had been understood before it was lost. The word permaculture was coined in the 1970s by 2 Australian researchers, Bill Mollison and David Holmgren, working from observations of traditional agricultural systems in the Pacific Islands, in Southeast Asia, and among the Aboriginal communities of Australia. The name was a compression of permanent agriculture, reflecting the core insight that had emerged from their study of these traditional systems. That it was possible to design a farming landscape that improved its own productivity over time rather than degrading it. That the relationship between farming and the natural world did not have to be extractive, that it could be reciprocal. The principles they codified under the permaculture name were not new. They were the principles that the traditional agricultural systems they had been studying had been applying for centuries. Multi-layer planting, edge management, water harvesting, soil biology cultivation, the closing of nutrient loops, the integration of multiple productive systems into a single coherent design. What was new was the synthesis, the explicit articulation of these principles in a form that could be taught to people who had no access to the traditional communities where they had once been transmitted. The regenerative agriculture movement that has grown from that foundation is now, in the second decade of the 21st century, a mainstream agricultural conversation. Major food companies have adopted regenerative agriculture commitments. Government agricultural agencies in multiple countries have introduced regenerative practice support programs. Investment funds dedicated to regenerative agriculture hold assets measured in billions of dollars. The language has entered the mainstream. Whether the practice follows the language remains one of the central tensions of the current moment. Corporate adoption of the term regenerative has not always been accompanied by the substantive practice changes that give the term meaning. The distance between a marketing claim and a genuine commitment to soil biology, water management, and biodiversity can be measured in audit reports, and it frequently is large. The movement has produced genuine transformation in the farms where it has been fully applied, and it has produced brand positioning in the boardrooms where it has been only partially understood. But beneath the commercial conversation, something real is happening. Research institutions that spent the 20th century developing and validating the chemical agriculture model are now publishing studies on mycorrhizal network management, on soil carbon sequestration, on the agricultural applications of biochar, on the efficacy of traditional companion planting systems. The scientific mainstream is asking the questions that ancient farmers answered empirically. The answers are coming back consistent with what the ancient practices had been doing for thousands of years. The lowest plateau of China was, by the 1990s, one of the most severely degraded landscapes on Earth. Centuries of agricultural erosion, accelerated by the removal of traditional watershed management practices that had regulated land use across the plateau for generations, had stripped the landscape to near barren slopes. Rainfall, which had once been managed by traditional terracing and vegetation cover into a productive agricultural asset, now tore through the landscape as erosive torrents, carrying topsoil into the Yellow River at rates that had turned it the color of rust. Communities that had farmed the plateau for 1,000 years were producing almost nothing from land that had supported them for generations. Beginning in the 1990s, a restoration project was initiated across approximately 35,000 square kilometers of this landscape. Applying traditional watershed terracing principles, combined with modern understanding of soil ecology and vegetation succession. Within a decade, the results were visible from satellite imagery. Vegetation cover had returned across large portions of the plateau. Erosion rates had dropped dramatically. Agricultural productivity on restored terraces had recovered to levels that made farming economically viable for communities that had been on the edge of abandonment. The restoration is now described as the largest successful land rehabilitation project in human history. The techniques were not invented by the restoration project. They were recovered from the traditional agricultural practices that the plateau communities had developed over centuries and that had been progressively dismantled by policy decisions that prioritized short-term grain production over long-term land stability. The modern project understood what the traditional practices had been doing in the language of modern soil science and hydrology, and applied that understanding at scale, with the resources that institutional support provided. The result was a collaboration between ancient knowledge and modern capacity that neither could have achieved alone. In South Africa, traditional companion planting and water harvesting techniques have been applied to land degraded by generations of colonial monoculture farming. The yields from traditionally managed plots have consistently exceeded those from adjacent plots managed with conventional inputs, not because the traditional practices are magic, but because they are adapted to the specific properties of the soil, the specific rainfall patterns of the region, and the specific pest pressures that have developed in that landscape over centuries. Martin Crawford's forest garden at the Agroforestry Research Trust in Devon, England, covers 2.2 acres and produces food from over 500 edible plant species. The design is a direct contemporary implementation of the multi-layer forest garden agricultural model practiced across Southeast Asia and Central America for centuries, a model that integrates canopy trees, understory food trees, shrub crops, ground covers, climbing plants, and root crops into a single system whose components support one another biologically without requiring external inputs. The garden has been producing food continuously for over 2 decades, its soil improving each year, its plant diversity expanding, its inputs declining. These are not experiments, they are demonstrations. Proof, operating at real scale in real landscapes, that the knowledge works where it has been recovered and applied. There is no clean ending to this story. The seed varieties that are gone are gone. The agricultural libraries that burned did not leave copies. The soil knowledge that lived in the hands and habits of farming communities, displaced by industrialization, died with the last generation that held it in practice. These losses are permanent, and acknowledging them honestly is part of what this story requires. But there are the Q&Ats, 3,000 years old, still flowing, still irrigating crops in landscapes that have watched empires rise and fall around them. There is the terra preta, still spreading in the Amazon basin, still demonstrating that what was built with knowledge outlasts almost everything built without it. There are the Hopi seed keepers, still growing the same corn their ancestors grew 2,000 years ago, still passing the seeds from hand to hand, across generations that have survived. Everything external systems have thrown at them. There are the researchers who followed an anomaly into a discovery, the farmers who chose tradition over subsidy, the seed savers prosecuted for growing vegetables too old to be legally registered, the scientists publishing in journals that practitioners in the field are beginning to read with the specific attention of people recognizing something familiar, the ancient farmers who grew food in the Atacama, in the Negev, on the frozen slopes of the Andes, in the underground chambers of Cappadocia. They were not performing miracles. They were applying knowledge. Knowledge that they had inherited, refined, and would have passed forward if the chain of transmission had not been broken by conquest, by economic pressure, by the specific arrogance that assumes the most recent way of doing something must be the best. That knowledge, where it survives, works. Where it has been recovered, it works. The agricultural future that the most thoughtful researchers are currently building: diverse crops, living soil, closed nutrient cycles, water systems that work within the natural budget of the landscape, farms that improve with every year rather than declining looks in its fundamental principles, like the agricultural past. Not a romantic reconstruction, not a museum piece. A set of principles, derived from thousands of years of careful observation, that the evidence keeps confirming as correct. The ancient farmers left the knowledge in the ground. The ground is still holding it. What remains is the willingness to look.